Cool. Hello, G-Focus. How are you doing, guys? Still keeping up? Cool. So my talk today is going about to be about service mesh. What are they? The hype that is around it. Is it true? Do we ever need them? So the short answer from now is not really. The long answer is the 1 hour that we'll be probably sitting for this talk. And before jumping into the technical discussion, I want to start with a quick story from history. And it's actually not working. Yeah, technical. OK. How about now, please? Cool. It's going to be the story of the phone. So following the invention of the phone by Graham Bell, the first phones were basically rented in pairs, which limited the conversation only between the parties that were operating at both ends of those instruments. So that's obviously isn't scalable. So in order to scale, we needed some means of interconnection to route the traffic between the destinations, between the caller and its destination. And for that, we invented what we call the switchboard. And we needed to hire what we call switchboard operators. And the job for the switchboard operators was basically to manually route the traffic to their final destination. So in order to call someone, I will actually pick the phone, not to ring the person I want to talk to, but actually to call an operator. And they will redirect me to the person I want to talk to. And the longer the call I want to make, the more operators I had to talk to. But even with that, things didn't actually scale well. More lines or more phones means more lines, more switchboards, and we needed to hire more switchboard operators. So we needed a kind of a new solution to move from the manual aspect of human interference to a more automatic and kind of a digital way where everything is routed automatically. And this is the era that we are living in, where we don't worry how the traffic is basically routed. It's routed automatically. Now, before you get bored, you may be wondering why I'm having this introduction. And the reason is, I believe we are kind of having the same evolution in the way we design and architect our applications. We started with monolith, and in order to scale, we started to break monolith down into multiple services. And the more services they have, the more complex it becomes to manage the communication between those services. Now the 5 seconds ad. I'm Mohammed. I work at Spotify as a backend engineer. And feel free to reach out to me at Twitter, pretty active if you have any question regarding Java, cloud native, or anything in between. Moving on. This is actually how the majority of architectures looked like in the 90s. All the components will tightly package into a single deployable unit, single flow of communication between the client and the server. But the problem with this type of architecture, some of them does scale, and some manage to scale. But in order to scale big for some users, it's going to hit you hard. So in order to scale, we started to break the monolith down into multiple services. And we needed some means of interconnection between those services. And for that, we used ESBs and MQs. And enterprise service buses, how many have the luxury of working with enterprise service buses before? Oh, a couple of hands, awesome. So the promise of enterprise service buses were actually legit if you read the text in the picture. And it seems kind of the things that we are trying to solve and the problem that we're trying to solve with the new technology that is cropping up. But back in the days, nobody picked enterprise service buses for ease of use or agility. Honestly, they were hard to operationalize, and the amount of coordination needed to deploy something was really hard. But it seemed back in the time as the right technology to solve our issues. Then, in the 2010s, the 2010s was about making everything smaller. We moved toward dump pipes, multiple services, probably written in different languages. But we stumbled upon different kind of issues. The more services we have, the more problems we faced. But it does scale really well. And you probably saw this picture before, probably in this conference, in a blog post, in a podcast. It's everywhere, preaching the amazingness of microservices architecture. But that is true. But bear with me here. And let's take the super awesome, really simple microservice architecture. And let's suppose that we have two services. Now I have a problem. This service X and service Y. Service X should be, if that works, service X should be this one, and this one should be service Y. And service X rely on service Y for some of its functionality. I probably need to name those services for the next time. Anyway, moving on. So service Y become unhealthy. And each call from X to Y generated some errors, but service X is actually incapable of handling error responses. So each call generated more CPU, and that means less number of threads that are available to handle new requests, which lead to service X become unhealthy as well. And the same thing happened for the services that are relying on service X, leading to bringing your application to its knees. And this is what we call, and you're probably already familiar with it, a cascading failure. And in microservices and generally in distributed systems, and this is how we look like trying to solve the pain and bring in our application up again. But we need to figure out the root cause first. But yeah, distributed systems at scale follows Murphy's Law, which basically say everything that can go wrong will basically go wrong. The more instances of anything you have, the more point of failures you have, and the more problems you will have. So if microservices distributed systems were easy, we won't have problems. But those are kind of all new challenges that more than 20 years back, two engineers, Peter Duce and the father of Java, James Kotlin, defined what we call the fallacies of distributed systems. And that's because, when we move it to a more distributed systems, we introduce it more points of failures because services are no longer stopping and starting at the same time in a predictable way, and so on and so forth. But those are the fallacies that we are making when we build our architecture. I know you all know them, but probably worth to go over them one by one. So we aim to think that the network is reliable, and we all know that this is not true. Things break. There are power supplies failures, router patches failures, DDoS attacks, and a lot of things that can go wrong. We tend to think that the latency is 0. And there is actually 7 orders of magnitude differences between a call that is made in memory and a call that is made over the network. We tend to think that the bandwidth is infinite. And nowadays, actually, this is not a problem. But keep in mind that even if the bandwidth become drastically better, the amount of data we send over the network has increased as well. We tend to think that the network is secure. And this is actually the fallacy that gets a lot of media attention. So unless you want to appear in the news the next morning, unfortunately not for the good reason, you should keep in mind that network actually is not secure. We aim to think that the topology doesn't change, and that's not true, especially with the containers and cloud era. We need some elasticity in the way we design our architecture. There is one administrator, not true. There is not one person that knows it all. Transport cost is 0, not true. If you had the chance to check your cloud bill, you know that the transport cost has a cost. And the network is obviously not homogeneous. And there are other challenges that came when we move it toward those loosely coupled distributed systems. Observing the interaction between those services become more and more complex. traffic management, doing things like A/B testing, canary deployment, and all the crazy thing with traffic management becomes more harder, especially to not impact client when we have now more points of failures. Securing communication and encryption the data flows that is going inside your cluster, like intra-cluster communications becomes more and more complex and challenging when we have those many binaries that are probably written in different languages. And finally, managing timeouts of communication failures, as we discussed previously, can lead to bringing your application to its knees, like the cascading failure we discussed. So when we know, or when we notice how it's critical the ability to control and secure the communication between service-to-service communication in distributed systems, we know that we are kind of under-tooled, and why running more than a few services is actually really hard. But as I mentioned before, those are not new challenges. We had them more than 20 years back, and we tried to solve them before. And we had a couple of tries. We had first this message-oriented middleware, the message brokers that was responsible for delivering messages. And we said, let's actually add resiliency features to the message-oriented middleware that we have. However, it turned out that it was like quite a bottleneck to add those resiliency features, and it was as easy as we expected. Then we said, we have the enterprise service bus, and yeah, let's add things like policies, service discovery to enterprise service bus. But ESBs, as I mentioned before, were hard by themselves. They were hard to operationalize. So it was by itself a complicated technology. And adding those network and infrastructure concerns will make it and made it a lot more complex. And finally, we noticed that it is not a good idea to mix business logic with infrastructure concerns. And then with the rise of API-first mindsets and the REST revolution, we invented a new piece of software infrastructure, which is the API gateways. Now, API gateways provide a single point of administration for the traffic coming to your business APIs. And yeah, we said, let's add those infrastructure concerns to the API gateway. And it did work, but for the outside traffic. But with API gateways, we didn't solve what we call the intra-cluster concerns and the intra-cluster traffic, and what we call the east-west traffic. And we started going down the path as we did in ESBs, which is mixing business logic with infrastructure concerns. The solution that worked really well, and probably some of you are using it currently, is to use client libraries. We started building client libraries and maintaining them and adding those infrastructure features and network features to those client libraries and packaging them and deploying them with your business logic. And it worked really well. A lot of companies are using it. But the problem with that, it requires a lot of investment to keep your whole fleet in the same version, or at least a backward compatible version. And we are mixing business logic again with application level concerns. And the next step would be to, as it happened with the phone, to move the infrastructure concerns to where they belong, to the infrastructure, to the network layer. And if you think about it, like as you can see in the picture, if you think about it, isn't it awesome if we as engineers can focus on doing what we do best, fixing bugs, improving the user experience, adding new features, and letting the operators handle the infrastructure and giving them in turn like configuration and controls to manage how the services interact, and leaving the infrastructure concerns, those network features, to where they belong, to the infrastructure. It looks awesome. However, this is actually not possible. It's impossible to change the network layers and the infrastructure as a whole. It's pretty much standardized. But the idea wasn't completely abandoned, actually. And what we thought to do is to implement the same idea in the form of sidecar proxies using the sidecar pattern. So the traffic or a service will no longer call its downstream dependencies, but the traffic will be routed first to a new piece of software engineering that is transparently inserted next to each service that adds the infrastructure and network features. And this is actually how the service mesh was born. So the service mesh is not a new technology, but it's a shift from where the implementation is located. So we're taking the network features and infrastructure concerns out from the application and putting it down a layer to where it belongs, to the infrastructures. And yeah, this is why I mentioned it. So taking the infrastructure concerns out of the application, putting it down a layer. And this is important in a sense, as microservices help it to decouple feature teams and help it to build general purpose cross-functional teams. Service mesh will potentially, and that's the promise and the hope, decouple operators from the release process, giving them in turn configuration and control on how the communication is done in between their services and control over the network. So as we're moving to a more declarative approach kind of things to set up our infrastructure, you can think of service mesh as a programmable framework that allows you to observe, secure, and connect your services. It helps to make the communication between your services a little bit more flexible, reliable, and fast. And this is how a typical deployment of proxies and service mesh will look like. So as the traffic is routed first to the proxies, it is the service mesh, or a typical service mesh deployment, will look as an array of lightweight proxies that are transparently inserted next to each application, and the traffic is routed to the proxies first by adding the desired infrastructure features. And a typical service mesh architecture would include two parts, what we call the data plane. So the data plane are basically the proxies and the sidecar, and they manage the traffic, either entering or leaving your traffic. So they're managing intra-cluster communication, as well as the ingress and egress gateway, which is the traffic entering your cluster and the traffic leaving your cluster. And the most important one for the service mesh is the control plane. And this is the management layer that provide control, policies, and configuration for the proxies. It takes a set of isolated proxies and turn them actually into a service mesh. And this is an important thing to keep in mind when we talk about the service mesh. If it has no control plane, it's not a service mesh. And be aware to not confuse service mesh with a mesh of services. So the service mesh is the management layer that enable us to control and configure the services and the network in your application. But the mesh of services are all the collection of services that enable the application to run. And you are probably by now asking, didn't we solve this already with containers and container orchestration tools? And the answer is not really. So containers provide as generic, non-language specific application lifecycle application management. But container orchestration tools are generic, non-language specific platforms that do a lot of stuff, resources scheduling, management, and the health management of your containers, and you know it. It's a talk by its own. However, Service Mesh tries to answer some needs that are not present and not answered by orchestration tools. So this table tries to highlight what are the core capabilities of containers and orchestration tools, and the missing service level needs that the Service Mesh is trying actually to answer. And another thing to mention is not only about microservices. Monolith, non-distributed application will be around for a long time, and Service Mesh, and that's the promise, will help in their modernization by providing facets to onboard your legacy infrastructural legacy applications into your mesh. But keep in mind that the more services you run, the greater the benefits of using Service Mesh. A quick overview of the Service Mesh ecosystem. You probably know the big three: Console, Linkerd, and SEO. But there are a lot of some others that are pushing the edge of technology and moving the community and the Service Mesh community forward. So Service Mesh, there are the typical features that are in all Service Mesh implementations. Quickly going over them one by one. So the traffic management features include routing with whatever you like, whatever metadata. Could be a header, could be some context-aware metadata, whatever. It enables us to do things like blue-green deployment, canary deployment, A/B testing, and all the cool stuff in a declarative way. Resiliency features include latency-aware load balancing, circuit breaking, retries, timeouts, and all of that can be done in a declarative way, YAML files. Security features. Service Mesh enable policies that define how the interaction between your services will be, which service can talk to which, and limit the communication between those services, and define which service has access to which, and that you can go more fine-grained and define other policies depending on your needs. And most Service Mesh implementation have certificate authorities that generate keys and certificates and enable you to do what we call mutual TLS between your services to encrypt the communication between your services, which is really cool and help to avoid a lot of problems. One of the cool features of Service Mesh is actually observability, and observability can be in the form of logs, events, and traces in the form of annotations and spans, metrics in form of gauges, histograms, and all the fun. And this is one of the great features, especially if you're lacking some monitoring. So Service Mesh will provide largely black box monitoring, but you can add desired features and do business monitoring as well. Time for a demo. It's going to be interactive. So I want you to grab your phone, scan the link, and it will send you to a cool sock shop. So have fun. I think the password are user password or user one password. You can log in, buy some socks, put your address. They won't be delivered ever. Is it done? Can I switch to the code? Cool. Thumbs up. Is it good? Cool. Let me move to the code, actually. So I have a microservice application that contains a lot of components. I'll get back to it in a minute. Probably I can show it here. Sorry for the trouble. This is actually, a Service Mesh application, contains a lot of services. And I have here this is actually my application. You're all here, right? You see the blue header. keep that in mind. I have also deployed the observability tool of Istio, and I have an Istio cluster running, and my application with the multiple servers are running as well. And if I go to Kayali, you can see that can we do full screen here? No? This one? No? You don't want to? Let me hide that one. Okay, you can see that with Kayali, it's kind of a dashboard for Istio. You can get an overview of how your microservices is. Now, this is still a simple application, but you can go wild. You can imagine how complex your architecture is. And you get a nice overview over your application. You can have, it's an Istio dashboard, basically, with all the information that you need about how your Istio cluster is. So that's the first things that we get with, by default with Istio, if you opt to it. And then we have monitoring tools out of the box. As I mentioned, black box monitoring. It is how my cluster is doing, the amount of requests I get, global success, everything. And I probably forgot to mention that I did run Istio here and deployed some stuff, but I'll get back to it. And other monitoring tools, so Istio or Grafana relies on Prometheus, probably already know it, open source time series database. We can go wide, you can do some requests. Like this one, I'm asking for the total number of requests, and you can see the spike. You can see the spike here, like the number of users when you entered. Pretty cool, right? And we have Jaeger. It's a kind of tracing application. When you are running microservice is really hard to debug. Whoever is running with microservices knows that they are really hard to track where the bug is, especially latency bugs. It's really hard to spot where the latency comes from. And this is what a tracing solution is. And for example, here I am having the catalog service. I have a service called catalog, and I can check all the traces. If that works, I'm connected. Yes, all the not many requests for that one. Probably I can check another one. The cards. Okay. It is slow, but yeah, you get the spans, you get the requests, and you can track the lifetime of your application and the cycle that went through. And yeah, this is the observability feature. Pretty cool, out of the box. Not a full lot of stuff to do, but you can extend it and add your business features. As I mentioned before, I deployed the application. I have a microservice application. We can do some cool stuff with the traffic management. So I have two front-end applications. If I get them, I have the V1 somewhere. Yeah, I have the V1, this one. I have the V2. And the difference between the V1 and the V2 is I will change the header here. So this one is no longer blue. I changed it to red. Even if they are deployed side by side, even if they are deployed side by side, why this one is crashing? Deployed side by side, I only got access, so I redirected traffic only to the V1. And I did that using what we call virtual services. So two things, the gateway and the virtual services. You can think of it, the gateway is where the traffic is redirected. So I'm redirecting the traffic from the V1 to the, for the front end to the V1. And the virtual service is what to do with the traffic when it arrives. What we can do actually is to do some cool things. Let me get it right. We can do blue-green. We can start with canary deployment. We can go there, canary stuff. We can say that I want that 80% of the traffic go to the V1 and 20% of the traffic go to the V2. So I have a configuration file here with virtual services where the traffic I want to be redirected, and destination rule, destination rule where the traffic to be redirected, virtual service, what to do with once it's there. So let me quickly pass this one to the virtual service. Is that right? Okay. Canary. Deployed. Now, if you hit the application, refresh the page, you will get 80% of the time blue, 20% red. Pretty quickly. Simple comment. Magic, right? No, did it work? A lot of blue, little red. Crashing? Damn, what I did. What I did. Okay, let me deploy it again. Oh, is it? Is it? No healthy upstream? I did something. Okay, is it running? Oh, too much traffic maybe. Oh, wow. Okay. Let me deploy it again. Sorry for that. Kubectl. Kubectl. Manifest, right? Manifest. Okay, bear with me for a second. Manifest, and it should be the front end. No, nothing. It should be here. Deploy. Oh, I forgot manifest. Manifest and front end one, right? Front end one, or what is called? Can you see it? Front F should be front end. Yeah, dip. Or yeah, could be anything. Let's deploy them both. Unknown command. Okay. Well, okay. Apply dash F. Demo guts, right? Okay. Unexpected. Oh my goodness. Is VC? Nothing. Should it work? Unchanged. How about now? Will it work? Okay, so I get the red. One of the services is having a bad time. I don't know which one. Gosh. Okay, back to life. Can you try now? Please not break it again. Too much traffic. Amazing. So, will you be using service mesh? Definitely no after this talk. It's crashing again, right? Oh, gosh. Too much traffic. Anyway, yeah, so, trashing again. Goodness me. Wow. So, don't test, I'll be testing. I didn't size my cluster the right way. So the promise of the cloud, right? And this is going live, right? It's recorded live. So amazing. Can it be edited afterward? Please work? No. And healthy upstream? Never. It will not work. No. Something is wrong. Yeah. Okay. Yeah, that's true. Let's. Good point. Let's forward all the traffic actually to the V2, right? Let's check. No, not this one. Blue, green, or should be this one. Front end V2. No, not this one. It should be. Okay, it's the blue, green. We'll switch all the traffic to the V2. Okay, so the blue-green deployment here of the V2, yeah, where I'm switching all the traffic to the V2. So now it should be V2 and healthy. But I did wrong. Yeah, thank you. V2. Please. Okay. Not really. Yeah. So yeah, something is weird with the. Yeah, it's crashing. Wow. That never happened. Wow. Woo. So yeah, the demo is failing hard. Probably. I would be happy if Google is down. Then I can blame them. Okay, what I wanted to do. Yeah, I wanted to mention some resiliency thing, but yeah, my application is not so resilient, so never mind. So, back to the slides. Gosh. 100%. Do not use service mesh ever. Okay, so yeah, I wanted to. A lot of people are using SEO, that's why I wanted to demo SEO, but now you know, yeah, they are in trouble when running SEO, especially with a live audience. The moment they run to production, they fail. Do you need a service mesh? Quick answer, no. Uh, Actually, it depends. It depends on a lot of things. If you manage to get it right, and your containers are running and not looping in a infinitely crash loop, there are a couple of scenarios that make sense to use service mesh, starting with modernizing your existing infrastructure. As I mentioned it before, not all applications will be containerized. Some of them will be either in VMs or bare metal or somewhere. So service mesh, the promise here will help to modernize an infrastructure and onboard this old legacy application to the mesh without them needing to adopt a new architecture like microservices or move to the cloud or adopt containers and Kubernetes. Another interesting use case to use service mesh is the service sprawl. If you have some microservices and a lot of services and you don't know how well those services are doing, using the observability feature of service mesh, it can help you to understand where the bottleneck is and design properly, and then have an understanding of your architecture. Another interesting use case is the monolith to service migration. If you want to pull out a functionality from your monolith, you can combine both observability feature and traffic management feature of service mesh to do shadow loading traffic, test your application, see if it matches the same functionality that it was in the monolith, and then gradually route traffic to it until you gain confidence and it's matched 100%, and then stop traffic to the old monolith. Another interesting use case is the release bottleneck, if you are not confident over your releases. Now, you probably noticed it in the failing demo that, yeah, you can route traffic gradually. You can specify some metadata to route traffic. You can select some users and then route traffic by percentage gradually and then roll it out. So if you don't have confidence of your release process, service mesh can help you with that. Debugging microservices. I mentioned debugging microservices is really hard. It's crazy, especially if you are on call and you wake up at 4 a.m. in the morning. So having monitoring tools in place is good, and monitoring observability features comes after the box with service mesh. And finally, chaos engineering. This is an interesting, if you're interested in adopting it. If the demo worked, you could return, you can insert delays, introduce or return errors, or limit, stop traffic to your service, and you can start gradually. We all know the things that we know about application, and we know that we are missing some information and how the system will react if things go wrong. But then the things that incidents enable us to do is like knowing the unknowns, the unknown unknowns of our services. So like adopting chaos engineering would definitely help in that. And we can do that easily with service mesh. You can return 500s, introduce delays, and so on. An interesting graph from our friends in Nginx, where they mentioned that as the complexity of your service grow, service mesh becomes a more realistic approach to adopting resiliency feature of service by service. And they also mention it as the technology matures, like the service mesh technology and the ecosystem is growing, the tipping point for adopting service mesh will basically go down. Another couple of graphs from our friends in Kinvolk, yes, they run a benchmark for SEO and Linkerd comparing to running the application in bare metal. And you can see the overhead in terms of latency, memory usage, and CPU. So adopting service mesh comes with a cost. But we believe in the community that as the technology matures, those graphs will comes down gradually, but it has a cost. And also, there are other type of costs. Think about the architecture lock-in. We are taking the infrastructural logic and the network features out of the application, putting them into the infrastructure. If things didn't work for you, then rolling back could be in some scenarios really hard, nearly impractical. So keep in mind that there is a cost related to architecture lock-in. Think about also the learning curve. Service mesh is relatively a new technology. So your team will need time, and you need time to understand the technology, play with it. You will have problems, as we had in the demo, so you need time to understand what's happening and design properly for it. And and also think about the environment drift when you are moving to service mesh. Final slide. Service mesh, as we mentioned, is a new technology implementing art patterns. Hopefully, it will help you to observe, secure, and connect your microservices. That's the promise. If you are considering microservices, don't do it yet. Wait. Wait, do your homework, search for the right technology, and then wait a little bit until you are pretty sure that you need the service mesh. When you are 100% sure, start small and then grow gradually so you learn as you go. And with that, I want to thank you. There are a couple of links there. Today's demo, the failing one. You can find it online. It's working. Wait a minute. Okay. I was about to say thank you. Okay, did it work? No, never. Okay, is it probably... Okay. It just insists to not work. That's embarrassing. Okay, so I will run the whole thing, actually. Hopefully. How about now? Can you help me? So yeah, it's available on GitHub. It's a self-walkthrough tutorial that covers a lot of SEO and service mesh functionalities. All what we have mentioned. You can deploy your application. You don't have to do it online. You can like install some GKE cluster or Kubernetes cluster in your local machine and play with it. Traffic management, resiliency, security features, and observability, all in this self-walkthrough tutorial. And probably you will run into the same issues as I had. It did work. Now, okay. How about, let me try. 8030, okay. This one, yeah, it's deployed. Blue-green, let's deploy the red version. Drum rolls, will it work? It should, right? Boom, red. Okay, cool. Let's try the canary deployment this time, right? We said that. Could it be the traffic that was messing with me? Okay, I should be back to green for most of the traffic. No, red? Yeah, blue, and you should get red sometime. Okay, so that was the, yeah, it's working. I can't believe it. I know, thank you. but I still need to figure out. I mentioned resiliency features, right? So we can introduce delay like this one. So I will introduce, let me show you actually very quickly, fault injection delay. So I will introduce 5 seconds delay to the catalog service. I have a couple services, one of them that shows what I'm selling in the catalog. So if I press this one, if I try to refresh the page, it should take 5 seconds until it render back. And this is a nice thing if you want to adopt like chaos engineering. You can, as I mentioned, introduce delays, and you can even do retries or send 400s, 500s, and since box. Okay, and as it did work, I will not stress it any longer. Just end it in a happy tone. Thank you. Yeah. And here are the links with interesting blog posts if you want to hear more about the service mesh. Any questions so far?